Thank you very much. Can everybody hear me? You can hear me? Okay, good. Thanks to Daniel for inviting me. My first time at the university in Toronto, giving a talk, and had some really fruitful interactions with colleagues here earlier this morning. So as Daniel said, my name is Mishkat, and I will be speaking about lasers for sound. Before I run out of time, I should acknowledge that this is a collaboration between my theory group at the Rochester Institute of Technology, or RIT, and the experimental group of Nick Vamivakas at the University of Rochester. And Nick and I, along with another collaborator, put together a sort of high-level, meaning easily accessible, introduction to this general area, which is called levitated optomechanics. I hope that will be clear why that name is used by the end of the talk. So this was published a few years ago in Optics and Photonics News, but if any of the students want me to share the PDF, please let me know. I'd be happy to do that. This is an image from Nick's lab of the flying laser for sound. And the flying laser itself is actually this little nanoparticle here. Is there anybody in the back who cannot see this nanoparticle? Okay, that's why it's called nano. So it's levitating in the air because it's held in place at the focus of an optical beam. You can't really see the beam because the entire apparatus is inside a vacuum chamber from which most of the gas atoms and molecules have been evacuated, so there's not much for the light to scatter from, but it does scatter from the nanoparticle. And these two black casings basically include lenses for focusing and defocusing the beam. So just to give you some quick background, this is a picture of RIT in the high temperature regime, shall we say. And we have 20,000 students, about 1,000 faculty. The physics department has about 40 full-time faculty. We offer a PhD in astrophysics, but not yet in physics. Hopefully that will change. We have recently started a master's, and it'll time evolve for a couple of years, and hopefully we'll start a PhD. So I mostly work with postdocs and undergraduates. These are the postdocs. The calculations and theory that I will be presenting today was mostly worked out by Brandon, Wenchao, and Pradeep. If time permits, I'll talk a little bit about Kevin's contribution. And these are our collaborators. The University of Rochester is a few miles down the road. This is Genesee River, and that is Lake Ontario, which separates us from Toronto. And this is Professor Vamivakas, and all the data that I will show was acquired by his students, Levi and Robbie. So this is the plan for the talk. I will give a longish introduction, keeping in mind the diversity of physicists in this audience. Let's speak a little bit about our theoretical predictions and their experimental confirmation, and then I will conclude. Most of the material covered in this talk can be found in sort of the first paper we wrote in this subfield a few years ago, and more recently a paper that appeared earlier this year. So we will be speaking about lasers, as the title mentions, and I thought a good place to start would be to remind you of the timeline of the optical laser. By the way, how many people, theorists and experimentalists in this audience, work directly or indirectly with lasers? Can you please raise your hands? Show of hands. Okay, very good. That's a substantial minority. And can I ask if there's anybody in the audience who's never used a laser pointer? Very good. For the purpose of this talk, all of you are laser physicists. So the laser was invented in 1960 by Ted Maiman, who is shown here with the first laser he made using ruby for the material. The quantum theory of the laser, which will be a little bit important for our exposition later on, was followed soon after and was put in place by Haken, Lamb, and others. Currently, lasers are a $10 billion market, very important. And of course, there have been multiple Nobel Prizes. In fact, Springer came out with a biography of Maiman last year. It's called The Laser Inventor. And there is an addendum at the end which lists 38 Nobel Prizes in physics and chemistry which are directly or indirectly related to the laser. In particular, in the context of this talk, I will be referring quite extensively to the 2017 Nobel Prize and half of the 2018 Nobel Prize. And I'm actually very grateful to Daniel for allowing me to speak today, because the Nobel Prize in Physics for 2019 is going to be announced at the earliest on the 8th of October. So if I came next week, it might have been too late. The buzz would have been about the latest Nobel Prize. I couldn't get your attention using these advertisements. Okay. So let's jump into the 2017 Nobel Prize, which, as you know, was awarded for the observation of gravitational waves. And this observation was carried out using a device called LIGO, the Laser Interferometer Gravitational Wave Observatory. And from the perspective of my talk, LIGO is a cavity optomechanical device. And let me explain why we think of it that way. These are highly reflective mirrors which can confine light for quite a while before it leaks out. So each of them forms a cavity. That's the source of the word cavity in the title. Opto, of course, follows from the fact that we inject laser light and detect it as well. And the word mechanics is involved because these mirrors are actually not pinned down in position. They are suspended like pendula, so they can move. And the idea is that as the gravitational wave passes by, it induces a path difference between these two arms. And that path difference can be translated into the interference of the light that goes down each arm and comes back out and is detected here. And you can actually see the signal on this detector ring along with the gravitational wave. And this is a very complicated experiment, of course. What I would like to bring to your attention is that in about a second of measurement time, LIGO can sense a path length difference between these two arms of the order of 10 to the minus 18 meters. This is an extremely small number. It's about 1,000th of the radius of a proton. Okay. So this idea of using light or photons to sense mechanical motion or vibration or phonons is actually a dominant theme in cavity optomechanics. LIGO, of course, has arms that are about 4 kilometers long each, but you can replicate the same physics with some loss in displacement sensitivity on a reasonable setup, on a tabletop in a reasonable sized lab. And people do it and measure all kinds of physical variables and parameters that they can couple to the motion of these mirrors. And such variables might be magnetic fields and electric fields and gravitational fields, velocity, acceleration, temperature. It's actually big business using this kind of platform to do sensing. But to go back to this idea of using photons to control phonons, which is sort of the theme of my topic today, this is an interesting idea because both of them are realizations of the harmonic oscillator. Photons are the electromagnetic and phonons are the mechanical realizations. The electric and magnetic fields corresponding to a photon are analogous to the position and momentum of phonons. And so, after all the reasons I gave you why a laser is an important object for photons, I think it's quite justifiable to ask if we can make a similar device for phonons. And that's the specific question that I'll be trying to answer in the rest of the talk. To motivate this a little bit more concretely, I'm going to use a basic paradigm that is simpler than the LIGO layout I showed you, but encapsulates the basic physics and consists of nothing more complicated than just two highly reflective mirrors facing each other. Okay? And most optical labs possess this instrument. It's named after its inventors, Fabry and Perot. And the interesting modification to that, which optomechanics involves, is that we now give one of these mirrors a mechanical degree of freedom. So here the mirror is suspended like a pendulum, so it can oscillate harmonically back and forth along the line joining these two optical components. Now, the idea is to try and get some of the photons from a laser inside this structure, and let's pretend that the oscillator is initially at its equilibrium position. We know the photons can make it in if the length of the cavity is an integer multiple of lambda over 2. And in this picture, that integer is 3. So we have 3 half wavelengths of the electromagnetic wave fitting inside the cavity. Fine. Let's now ask what happens when the photons make it in and then they reflect off this end mirror. Their linear momentum gets reversed. And that happens again as they come back after a round trip, and again and again. So there is a rate of change of momentum per unit time, or force. The radiation inside the cavity actually exerts a force from left to right on this mirror, so the mirror moves further away from the laser. But when the mirror moves further away, the length of the cavity changes. We are no longer on resonance. Fewer photons come in. There is less force, and the restoring force due to the pendulum support moves the mirror back. But when it moves back, the length is closer to resonance. More photons come in. There is more force. It moves back to the right. So in this crude description I'm giving you, I'm trying to sort of bring out the fact that there is a feedback loop between the optics and the mechanics that is happening here. I'm giving you a very crude description of what is technically called the static recoil of the mirror, and I'm completely ignoring the dynamics of the fact that the mirror is oscillating. Okay, but from this schematic, we need nothing more than to keep the word feedback in mind. That's going to be operative as we move on. A couple other things. In many cases, it's enough to model the motion of this oscillator classically. But in some cases, we are interested in its quantum motion, so we have to think of it as a particle in a parabolic potential. Its energy states are discrete. The lowest energy state is called the ground state, and so on and so forth. So this is actually a spectacularly successful paradigm for both looking at gravity, like the example I gave you, and also at quantum mechanics, as I will give you some examples later on in the talk. And I don't want to say that this is a bad thing, but there are a couple directions where you can make improvements, and I will talk about 2 of them. The first area of concern is this tether or clamp. Most mechanical oscillators are attached to some kind of substrate or support, and that is a channel for thermal noise to come in and interfere with the motion of this object. If you're trying to do quantum things with this object, this is a channel for decoherence and damping, which you would like to avoid, number 1. Number 2, this force that we talk about, if we go through the calculation, you will probably not be surprised to learn that it's proportional to the intensity of light present inside the cavity. Okay, so the radiation force is proportional to the optical intensity, and then the interaction between the light and the motion of this material piece, or the light-matter interaction energy, is simply this force times the displacement of the mechanical mirror. Okay, so the light-matter interaction is the optical intensity times the displacement of the mirror. And the cause for concern is that the presence of these 2 mirrors actually confines us to a form of the light-matter interaction which is very specific. And the question is, can you make a modification to this device so we can engineer the light-matter interaction more freely? And if you do that, can you get useful and interesting physics? And I'm going to try to convince you the rest of this talk that the answer is yes, you can. So we can get around the clamping problem by leaning on Art Ashkin's invention, which earned him the Nobel Prize last year, half the Nobel Prize in physics. And I had to be careful about that because last weekend I was speaking at Waterloo. So what we do is we now use a Fabry-Perot with 2 mirrors which are bolted down, and we excite it with a beam which, if the mirrors are curved, is going to go through a focus. And Art Ashkin showed that you can trap a nanoparticle at the focus of such a beam, and I'll talk about it in a little bit more detail in a second. But essentially, to a very good approximation, the motion of this nanoparticle about the focus of the beam is that of a simple harmonic oscillator. Okay, so we have our optomechanical situation back. We have an optical mode. We have a mechanical object that's going back and forth like a harmonic oscillator. We do not have any mechanical clamping. All this is optical clamping. Of course, there's still some decoherence due to the fact that photons are getting scattered randomly off of this nanoparticle, and that's going to induce some kind of heating, but it's typically much less than straight-on clamping or tethering to a support. Second issue about the form of the light-matter interaction now raises the question, can we throw away the cavity and still recover some interesting optomechanical effects? And the first person to show this was possible was Lucas Novotny, who in 2012 performed a very elegant experiment. He took a laser beam, focused it down, and trapped a nanoparticle at the focus. So far, nothing new. Art Ashkin has taught us how to do this. It is also known how to take photons scattered by the nanoparticle from this beam and interfere it with photons that do not scatter from the nanoparticle. And in this interference pattern is contained information about the motion of the particle along the 3 Cartesian directions in space. So the experimentalists can measure the position of the particle. And Lucas did that. And then he just fed that information to a device which went to another device which modulated the intensity of this beam. So now we have feedback. It's active feedback. We have thrown away the cavity, which used to provide passive feedback. But now this active feedback is under our control. We can use any transfer function we like and are interested in to realize physics on this platform. Okay, so let me describe this a little bit more in detail. Any particle in this situation will feel 2 kinds of forces. The first kind of force is what you might expect from the beam. Because the beam moves from left to right, you might expect it to push the particle to the right, and that's exactly what it does. And that force is called the scattering force. For these particles that I will describe and that are used by our experimental collaborators, the radius is typically 50 to 100 nanometers, and that's much smaller than the wavelength of this trapping light, which is typically a micron, 1064 nanometers. And it turns out that for such small particles, the scattering force is negligible. What determines the dynamics completely is called the gradient force. And this was also researched initially by Ashkan. And the explanation of the gradient force comes from the fact that the particle is a dielectric. It's neutral, but it contains equal amounts of positive and negative charges, which can move around at least a little. So this electric field from the laser induces a dipole moment, which then interacts again with the electric field. So the gradient force is a conservative force. You can write a potential for it, and the potential energy is exactly what I just described. It's a dipole interaction. The dipole is induced, so it's proportional to E, so you get 2 powers of E here. And if you are using a Gaussian beam, which looks like this, and the oscillation amplitude of your particle is not very large, so you can Taylor expand this exponent to first order, retaining just the quadratic term, you find that you get a harmonic potential. This is what I meant by the particle behaving essentially like a pendulum at the focus, or near the focus of this optical beam. And this is true in all 3 directions, X, Y, and Z. If the amplitude of motion is not very high, the motion along these 3 directions is independent. They decouple. And for the rest of this talk, I will basically talk about one-dimensional theory and one-dimensional experiments. Okay. I would like to emphasize that the intensity of the trapping laser is really the only knob that the experimentalists have for influencing the dynamics of the particle. Okay? You can change things like the background pressure, temperature, but those things change over very large, time scales very large compared to the dynamics of this particle. And so to actually get some interesting physics out, you have to do something to the trap intensity. In fact, what we do in this loop after acquiring the position information and before coming to this modulation is kind of critical, and I will describe it in 3 different ways. So the first way I'll describe it is just using a picture. The second way I'll describe it is I will write some math on the board, but it's going to be a heuristic explanation. I'll wave my arms a lot. And then finally, I will present a microscopic quantitative model of the configuration that we actually use to extract predictions. So all the feedback physics in this talk is related to the physics of a child moving on a swing. We know if we push at the right time, we can amplify the motion of the swing. And this is going to be the amplification in our laser. You know, laser stands for light amplification by stimulated emission of radiation, so that's the amplification. We also know that if we push at a slightly different time, we can slow down the motion of the swing and reduce its amplitude. And that's going to be analogous to cooling. And it's kind of a little bit non-intuitive why you need to cool. It's like adding loss to your laser. But it turns out that in our case, cooling is necessary not only to retain the particle in the trap, but also to supply nonlinearity that is very essential for a laser. Okay? So let me walk you through how these two different parametric feedback mechanisms work. It's kind of important that we heat and cool, or amplify and cool, but it's also important that they have different parametric dependencies on the oscillator variables. If they just have the same exact form, then they just cancel each other. You will add noise to your feedback, and that's all you do. So for amplification as well as cooling, I told you the experimentalists can measure the position of the particle. Then they take an electronic circuit, which gives the time derivative of the position, so they have the momentum. So now you have both the dynamical variables of the oscillator measured, and then you modulate the intensity of the trap laser so that the potential for the nanoparticle varies according to the ratio of momentum to position in the first case and the product in the second case. This number, this quantity in front, allows us to decide whether the feedback is going to be positive or negative. It also allows us to make sure that the second term is never more than 10% of the first term. So we don't lose the particle, we don't destroy the trap, we just modulate it slightly. Okay. Now, in the spirit of doing a very kind of heuristic explanation, I can take the derivative of this potential with respect to position with the right sign to get the force. And you will get two terms. The first one is the linear restoring harmonic force. That's trivial, I've not written it. The second term will give you a damping, a linear damping, okay? But if you switch the sign of this constant, then you'll get a linear amplification, and that's what we use in our theory proposal and the experiment. In this case, you will get also a damping because it's always opposite the momentum of the nanoparticle, but now this damping is nonlinearly modulated by the position of the particle. So if I were to plot the magnitudes of these two forces versus the displacement of the particle, they both vanish at the classical outer turning points of motion because they are both proportional to momentum. But this force is very big as the particle zips through the equilibrium position with the maximum velocity it can muster, while this force actually goes to zero because it's proportional to the displacement squared. Okay? Now, I will show you the result of a fully quantum mechanical calculation, which takes about 40 pages of LaTeX, is tedious, long, but sometimes presents interesting conceptual challenges. And this is sort of the preamble to that big equation. Let me just at least describe the elements that go into it. So we have a Hamiltonian for the kinetic energy of the nanoparticle, which is here. That's familiar. We also write the total energy of the electromagnetic fields involved. And we write the interaction between light and matter averaged over the volume of the nanoparticle here, where we assume that the nanoparticle is just a linearly polarizable object. The polarization is some constant times the total electric field it sees. Now, there are a number of electric fields involved. One is the electric field of the tweezer itself, the trapping beam, which is polarized in such a way that it just traps the particle and ends up in a beam dump. Then there is a cross-polarized weaker beam, a probe beam, which actually measures the x, y, and z motion. And that information is fed back to modulate the trapping beam intensity. And then there are all the modes into which the nanoparticle scatters photons, which is why we could see its picture on that first slide. And the total field is the sum of these three fields. Having written this Hamiltonian, we then crank the machine to carry out a pretty much standard calculation in quantum optics. We assume that these modes are weakly coupled to the nanoparticle. We are only interested in one direction of motion, so we trace out all the other directions of motion. We're only interested in the nanoparticles. We trace out the dynamics of the fields. To make contact with experiments, we include suitable terms for collisions with the background gas, and we ensure that this feedback accounts for the disturbances that it causes in this system, because that's what happens in quantum feedback as opposed to classical feedback, where you can assume that what you've measured is not changing as a result of the measurement. Now, these two pieces can be bought off the shelf, by which I mean there is existing literature which you can adapt, which we did adapt to our specific model. And now I will show you the big equation, which is here. It is, for those who are interested, this is a master equation for the density matrix of a nanoparticle oscillation along a single direction. If you don't feel like looking at this column, ignore it, please. But I'd like you to run your eye down this list, which details all the physical processes that have been accounted for in the dynamics. So this is just the unitary dynamics. It's just the harmonic oscillation of the nanoparticle. These two terms account for the fluctuations in position and momentum which occur because of the collision with background gas and the recoil from the photons of the tweezer and the probe. This is a damping, again, due to motion in the viscous gas provided by the background molecules. The two types of feedback that I described to you and the disturbances they cause. And like I said, these pieces are largely available from the literature, and we just had to adapt them with some appropriate modifications. So now I'm going to talk a little bit about how the simultaneous presence of cooling and amplification leads to a phonon laser, but I'm going to work my way up to that topic. Just to remind you one more time, there's in condensed matter physics the picture of phonons as collective excitations of atoms arranged in arrays which are interacting, okay? I'm not going to talk about that situation. I'm going to talk about the situation where a phonon is the excitation of the center of mass oscillation of a single object. I've shown it as a mass on a spring here. It's basically the nanoparticle in the tweezer that I'm talking about, okay? So there has actually been a lot of work in the solid state on phonon lasers, and I wouldn't be able to cover it in this talk, even if I wanted to. I'm going to focus on this optomechanical aspect of phonon lasing, and there has been some early work. In 2010, Kerry Vahala published his review, and this is a largely classical treatment. In 2012, these authors published a theory Fizerev letter showing that the typical equations of optomechanics can be made to look like the typical rate equations of laser physics. And they offered a definition of what a phonon laser is: optomechanical systems in which optically furnished gain enables self-sustained mechanical oscillations. They're properly called phonon lasers. And I hope you'll see why I'm quoting that in a little bit. What does this mean? Let us look at some data from the laboratory of my collaborator, John Lawal, at NIST Gaithersburg in Washington, D.C. He has a cavity, the Fabry-Perot type cavities that I was referring to earlier. One of the mirrors in his cavity is simply a highly reflective mirror, nothing fancy. The other piece is a highly reflective grating which can flop back and forth along this line joining the two mirrors. And he can actually excite hundreds of mechanical modes on this floppy grating by driving it with a beam of light. Now, this is the picture that kind of explains what a phonon laser is. This is on the horizontal axis time, and on the vertical axis, the mechanical amplitude of one of these mechanical modes, okay? And this is the threshold point. Below threshold, the motion of this mechanical degree of freedom is Brownian. It's thermal. Above threshold, there is an exponential increase or amplification in coherent oscillation, followed by saturation. Okay, so I'm slowly working myself into the list of things that a laser typically, list of characteristics that a laser displays. Okay, now this is a sort of textbook description of what an optical laser does if you replace mechanical amplitude by electric field. Okay, this is the analogy that we spoke about earlier between photons and phonons. John sees more laser-like phenomena. He sees, for example, mode competition. He sees a blue mode come up the same time as a red mode. Eventually, the blue mode dies away. There's not enough amplification for it to persist while the red mode stays. And some of the data, a lot of the data in his paper looks very much like early studies of lasers, homogeneously broadened lasers by Lamb in the 1960s, but I won't go into the details of that. But this is in a clamped system with a cavity. Remember, we don't want clamping and we don't want cavities. So what about in these levitated, unclamped systems? Here, the pioneering paper came from a collaboration between Kari Vahala, who was visiting from Caltech, the Max Planck Institute for Quantum Optics in Munich, which is, of which the director is Ted Hench. You might remember Ted Hench because he won the 2005 Nobel Prize for figuring out how to make optical frequency combs, along with Jan Hall. And Hench has an ion trap with a single magnesium ion, which is confined by electrodynamic fields, so no mechanical clamping there either. And it oscillates pretty much like a simple harmonic oscillator, but now it also has this internal ionic structure with a ground state, several excited states. And they were able to get phonon laser-like behavior out of this ion by using two beams, one of which cooled the motion and the other heated the motion. I won't go into the details, but the upshot is that you can see the exponential increase in the mechanical oscillation of the ion, which they can image as a result of this. And this happens across a threshold which they can measure. This paper by Hench was published in 2009. It's 2019 now. It's 10 years. The questions regarding lasers have sharpened since then. And the reason I mention that is when we tried to implement a phonon laser, we immediately found ourselves asking the question, what is a phonon laser? What characteristics exactly must it display to qualify as a phonon laser? And then we had to take a further step back to answer the question, what is a laser? How do you define a laser? So let me work up to the answer. A simple way to think about lasers is to think of light as consisting of waves. A source like the sun or an incandescent light bulb sends out waves, which, if an observer was detecting them here, would seem like one wave comes in with its trough hitting the detector, the other one comes in with its crest, and the third one comes in somewhere in between. So there is not a clearly defined phase relationship between these waves, which are all coming into the detector at the same time. However, for a laser, the detector will see essentially all the waves coming in sync. Okay, this is with all the crests and the troughs lined up. And optical physicists often call this phenomenon of being in lockstep coherence. And laser light is said to be coherent light, and the other sources are said to be incoherent. And that's sort of a simple-minded way of looking at it. A real laser might look much more complicated. This is a helium neon laser, one of the earliest lasers invented and now often used in teaching laboratories. So the helium neon laser in this case includes a Fabry-Perot cavity. There are two mirrors, one at the back here, one at the front. They're usually highly reflecting, so the photons go back and forth, and sometimes they leak out of this end. There is a lasing medium or gain medium which supplies the amplification, and it's excited by a pair of electrodes. You have the anode and the cathode. If you set a voltage across them for a sufficiently high voltage, you can get a current going, which means there's a flow of electrons. The electrons knock the helium atoms up into an excited state. The helium atoms collide with the neon atoms. The neon atoms jump down from their excited state and emit photons at various wavelengths. The one at 633 is a strong transition, and that accounts for the typically red wavelengths coming out of the helium laser. As the 633 nanometer photons go back and forth between the two mirrors, they induce more and more of the neon atoms to emit yet more 633 nanometer photons, and this is the phenomenon of stimulated emission that was posited by Einstein. So This is just an example, but if you look at the literature, people have their own idea of what a laser should be. Typically, a person expects a laser to be what the laser can do for them. So what I mean by that is if you talk to an industrial micromachinist, they might only care about the power in their laser, maybe about the mode a little bit. If you talk to spectroscopists, they might only care about the line width of their laser. If you talk to a quantum communication specialists, they might only care about how much information can be carried in the laser. So how do we decide a set of characteristics? So the task was made easy for us because we decided to submit to a journal called Nature Photonics, which actually has an optics laser checklist. Okay? This is a questionnaire which you need to fill out if you think you've made a lasing device before your paper goes out to review. Okay? And although it's nominally an optical laser checklist, they made us fill it out, and it's actually available with the online version of the paper. So according to this checklist, a laser is many things, not just one. And these are all the characteristics it needs to have. There has to be some evidence of stimulated emission. The output needs to show a threshold. Line width has to narrow across the threshold. Either coherence or polarization need to be accounted for. I put both of them there. And there has to be a well-defined output beam above threshold. You can argue with this list. I'm sure many of you don't agree with it. There are certainly published exceptions. The reason I'm showing it to you is that the vast majority of lasers follow this checklist quite well. There are exceptions, but the vast majority of lasers. One thing I'd like you to note is that there is no mention of a quantized gain medium. And by that I mean, if you go back to the Heaney, these atoms are the ones that provide the gain, and they have quantized energy levels, and that's sort of normal in every optical laser. You have either gas or you have a solid-state crystal within this laser pointer that I'm using, but there's no mention of it here. And they launched this checklist experiment as a trial object in 2017 with consultation of the community, and it has stayed. So people agree with it to some extent. So now I'm going to run down in the remaining few minutes of my talk. I'm going to run down this list and show how our system follows or shows these four characteristics. These two can also be implemented, just takes more work on the part of the experimentalists and hasn't been implemented yet. So let's talk about stimulated emission. Is it there in our system? If we calculate the time rate of change of the probability P, that our nanoparticle oscillation has n phonons, we get a very complicated differential equation, which at first, at least to me, is not very intuitive. But we note that it refers to states with n, n-1, and n+1 phonons. So let's draw these states here. And once we do that, we find we can assign every term in this equation uniquely to either a single phonon or a two-phonon transition between these three levels. And in particular, we can look at the transition that leads to emission into the phonon field, meaning you had n phonons initially, and then you ended up with one more. And that's this process. And there, if you go in, you find you can tease out the different contributions due to the stimulated and the spontaneous emissions happening, because the stimulated emission depends on how many quanta were present initially. If there were more quanta, the driving due to stimulated emission is even more pronounced. The spontaneous emission part doesn't care how many phonons were there initially, and it's just independent of that number. Okay? So this is sort of theoretical proof that stimulated emission exists in our system. One point I would like to make is that the top line is our calculation, and this bottom line, these terms in the square brackets, I have copied from the standard textbook by Scully and Zuberi, who have a similar diagram. So we have a couple of extra terms, but otherwise we are pretty close to the textbook realization of a laser. Okay, let's look at theory and experiment now. I told you that the experimentalists can measure the position. You square the position and you average over the fast mechanical frequency and divide, multiply by the right units. You can get the number of excitations, or the phonon number. And from our theory, and this is the equation that I really like to show because it's compact and contains all the analogies nicely. And this is the equation for the rate of change of the mean phonon number, the same thing that the experimentalists can measure. The first term is nonlinear, and that's the typical nonlinearity that's contained in any laser. In the helium-neon laser, that's basically because you cannot excite these atoms indefinitely. At some point, they will saturate. The gain comes from the linear amplification feedback process we use. Loss is due to collision with background gas molecules, as well as the cooling. And the role played by this term in standard optical theory, it corresponds to spontaneous emission, but all the fluctuating processes in our system contribute to that. So let's solve this equation in the steady state. Let's set the left-hand side equal to 0. So you get a quadratic and the Phonon number. And then you solve it as a function of gain, and that's what I'm showing here. Horizontal axis gain, vertical axis steady state mean Phonon number. And you can see clear threshold behavior. This is experiment on top of theory now. And the 3 different values of the curves are for 3 different values of the nonlinearity. So we are showing that we have a threshold and it's tunable. This equation, although it's nonlinear, this differential equation, although it's nonlinear, can also be solved analytically. You get a tangent hyperbolic solution. And now we are showing the time dynamics of the Phonon number transient, also experiment in theory at the same time, for 2 sets of 2 values of this nonlinearity. And you can see a very nice Hench behavior as there is initial amplification of the mechanical oscillation followed by saturation, just like in John's system that I showed you earlier. We also see line width narrowing, but in the interests of time, I will not say too much about it. This is almost my last slide. Are we on track? Okay. I'm rushing to meet the deadline. So one of the nice things about the experiment is that you can keep the same nanoparticle for hours, if not days, in your trap, and you can run various versions of the same experiment with it. So you can build up an ensemble of realizations and build up essentially a histogram of energies. And this is what that histogram can be shown as. On this axis is the number of phonons. This is the probability that there are n phonons, the same p of n for which I showed you the differential equation. And this is time. So this is sort of the initial distribution, and this is the final distribution. Now, having access to the distribution is nice because then you can calculate any moment of the distribution. I already showed you what the mean does for that distribution because we have a nice analytic equation for it and solution. But you can also calculate the variance, the kurtosis, the skewness, whatever you like. With just the mean and the variance, you can calculate the equal time autocorrelation function of the energy, which is often used to characterize the coherence of the system. If you think back to the picture of the light bulb and the laser that I showed you, this factor tells us how well the waves are in sync with each other, okay? So on the horizontal axis is gain, on the vertical axis is this quantity G2 of 0, and below threshold, we have the textbook value of 2, which if you take a chaotic or thermal state and calculate, that's what you'll get. So this is the case of the light bulb or the sun. For values far above threshold, you get almost 1. And exactly 1 holds for the case when all the waves are perfectly in sync. That's called the coherent state in quantum optics. If you look a little bit more closely, you'll see we only have an approximation to a coherent state. So here, because the state is thermal, if you look at the statistics of the phonons, you will find they fit very nicely to a Boltzmann distribution as you would expect. Here, however, if you look at the distribution, you will find it's not quite Poissonian as it should be for an ideal laser, because in a Poissonian distribution, the variance is exactly equal to the mean. In this case, the variance is actually a little bit larger than the mean. But our theory shows that if we use lower pressures, then we should be able to get a pretty good coherent state. And that's what the experimentalists are working towards. I will now summarize with 2 main points that I'd like you to carry away. See, I can talk for hours. So, undoubtedly, the work of Vamivakas and Hench pioneered the construction of phonon lasers at the atomic scale. It's kind of interesting because we already know how to control these atomic ions and implement quantum physics on them. People build quantum simulators with them. People are trying to build quantum computers using these platforms. At the other end are these clamped cavity-based systems where you can also get phonon lasers, and we call them microscopic. It's much more difficult to see quantum phenomena here. And there are 16 orders of magnitude in mass between these 2 limits, and our work sits right in the center. And that's the regime I call mesoscopic. a regime where you have collections of about 1 billion atoms, like in our nanoparticle. And that's the place where currently people are trying to test quantum mechanics, whether sufficiently large superpositions of sufficiently massive objects lead to breakdowns of the predictions of the Schrodinger equation with some additional terms. The so-called collapse theories that have been proposed, they are testable in this region. Now, if you want to make a non-classical state for a moving object, not a bad idea is to start from a coherent state. This is what happens in optics. Squeeze states, Schrodinger cat states, they first start life as a coherent state coming out of a laser, then you put a nonlinear crystal in between and you get your non-classical state. So our work basically supplies, it forms a source of coherent phonons at the mesoscale. And we hope that more non-classical work can be done following ours. Second thing that I would like you to carry away with you is that although I have worked with this optical tweezer setup because it's nice for the experimentalists, it's going to be modeled very cleanly with theory, our technique is very general and applies to any harmonic oscillator. All you need to be able to do is to measure the position and feed back to modulate the spring constant in a certain way. So you could use this to build coherent states for single electrons, for liquid droplets, maybe even for small biological organisms, which people have shown can be trapped optically. Thank you for your attention.